You can shut that if you want. All right, so we're going to talk about the scientific method, matter, classification of matter, measurement, density, percent, uncertainty, significant figures, and also problem solving. There's a lot of dimensional analysis problem solving in Chapter 1, so we're going to review through that. And so let's start off with the first topic, scientific method. The scientific method, I'm going to have a slightly different version than what's in our book. This is based on how I did science and how everybody else did science around me. And so what do scientists do? Or more specifically, what do chemists do? What's chemistry about, or what's science about? Or how about this? What is the definition of chemistry? Can somebody just give me the definition of chemistry? What is the definition of chemistry?
The study of matter.
Study of matter. And so how do we study matter, usually? When you study something, what do you do? Observe. Yeah, we observe it. Anything else? No, that's basically it. That's what scientists do. Scientists are good at observing nature. Right? Chemists are good at observing matter. They want to observe matter. In fact, when we observe, what we do usually, we take, qualitative observations or quantitative observations. What's the difference between qualitative and quantitative?
Observe compared to what we're observing, I guess,
I'm sorry.
The quality.
The quality, yeah. It has to do a lot with the quality.
Yeah. I don't know what I'm trying to say. Sorry,
no, that's along the right track. Can somebody else clarify a little bit? The qualitative versus quantitative observations.
I think quantitative has to do
With numbers, yeah. Taking measurements. Oh, go ahead. Yeah.
Qualitative would be like shape or color or stuff like that, or like physical observations of it.
Okay. Well, physical observations can be quantitative too.
I mean, physical characteristics or no?
Well, even chemical characteristics can be qualitative. It's just the kind of the way you do it. We'll get into it in just a second.
Qualitative would be the depth of observation, whereas quantitative would be the amount, a larger amount.
Sort of, but not exactly. The qualitative is just kind of a rough measurement or rough observation, whereas quantitative would be a more concise measurement. We have a name for that. It usually has to do with something called precision. You know the difference between precision and accuracy? Precision and accuracy is also covered in Chapter 1. It's not mentioned in the text here. But have you heard those terms? Have you used the terms precision and accuracy? How would you use precision? Qualitative would just be, there are a lot of people in this room, right? But a quantitative would be, there are maybe over 50 people in this room, or being very quantitative or being very precise, we just count everybody in the room and then get the number, the exact number, or an accurate. You know what accuracy is? Accuracy is how close the number is to the true. So if I said, there are about 50, maybe there are exactly 50, and that was pretty accurate, right? But it's not very precise because I'm saying about 50, right? If I said there are 50 people in this room, then that would be more precise. Right? And it turned out maybe it's accurate, maybe it's not accurate. If somebody said there are 13 people in this room, well, that's being very precise because they're saying there's 13, right? But are they very accurate? No. So we have to get comfortable with those. in terms of our observations. But usually we observe nature. In observing nature, we take measurements. We measure properties. Actually, if you're thinking about chemistry, what is chemistry? It's the study of the properties of matter. And so what are the properties of matter? There are two properties of matter. They're the physical properties. Physical properties can be very precise too, very quantitative. For example, if you want to know what the boiling point of water is, you just say, oh, the boiling point of water is super hot. Is that very quantitative? No, that's very qualitative. The boiling point of water is 100 degrees C, 100.0 degrees C, 100.00 degrees C. What is the boiling point of water? How precise is it? Is it exactly 100 or roughly 100? So those are issues of precision. And so we have to get comfortable with this because, what do scientists do? They observe things. When they observe things, they want to be quantitative. They just don't want to say, oh, that's a lot of stuff. Oh, that's a lot of white powder there. Or that's a lot of liquid. They get away from that and be much more precise and hopefully more accurate too. Being precise isn't always accurate though. It depends on how your instrument is calibrated. But we take observations, we take a lot of measurements. And oftentimes those lead to, in nature, they lead to patterns or trends that are observed in nature. There's certain patterns. It's not totally random, right? These are patterns, trends. And from these patterns and trends, sometimes we can define those or describe those mathematically by a law. And so in physics, for example, if you take some physics, you'll learn about, Newton, right? Newton, and an apple fell on his head or something of that sort. I'm not exactly sure what the story is. It's been a long time since I read it. But from this observation of the apple falling, he took, it's not just an apple falling, but you want to be quantitative about this. How long does it take the apple to fall? What distance? Is the apple falling at a constant rate or is it accelerating as it's falling? And so you take a lot of measurements. And from those measurements, then you get some kind of pattern or trends and you end up with the law, Newton's laws of motion, right? We end up with that. And so we got an apple falling. Well, then he can predict, well, if it fell from a taller tree, based on Newton's law is just some mathematical equations, he can calculate how long will it take to hit the ground from an even taller tree, based on those patterns that are observed, and just figuring out, based on these patterns, we can predict other things, right? But scientists just don't want to stop at a law because, the next question is, why is it? Why is it falling down and where is it going to? If it didn't hit the ground, where would it eventually end up? If there wasn't something blocking it, where would it fall to? Would it fall all the way to the other side of the globe? Maybe somewhere in China? Is that where? Or maybe it'd shoot past China and go into space? Where is it exactly falling to? And so Newton's law, Newton's laws are great because we can do all these kinds of predictions, right? With this, but there's something more to it, right? And so that something more to it is this, the hypothesis and the theory. Where would you hypothesize that this would fall to? Or, or why? Or what would it be? Would it go, let's see, if it had a straight shot, would it go through the center of the Earth and out to the other side? Or where would it stop? Where is it being attracted to and what's attracting it? Yeah, and so somebody hypothesized there's something called gravity. It's a force of nature, right? Gravitational force. and come up with this theory of gravity, I guess we could call it that. And the theory of gravity is how two bodies attract each other. The pen's not just being pulled there, but it's also getting attracted to the moon and other bodies. It just so happens this is going to be the biggest attraction, which is going to overwhelm the others. And so there's a gravitational, where two bodies attract each other. That's a theory. And so, well, that's an example from physics, but what about from chemistry? Can you think of some laws in chemistry where the origin of the law is? One of the laws in chapter 1 is the law of conservation of mass, or conservation of matter. Matter is neither created nor destroyed, or mass is neither created nor destroyed, right? That law. Where did that law come from? And so we got the law of conservation of mass. Did that law of conservation of mass come from theory? We already figured everything out and then just kind of predicted that there should be this law? Or did it come from observations? It came from observations. What observations did it come from? Well, it came from like the burning candle observation. When you burn a candle, the candle's mass shrinks. Right? Where did that mass disappear? Well, it didn't really disappear because that mass was converted into a gas or gases. And if you weigh those gases, then you'll see that the mass that the candle lost is exactly the same as the mass that the experiment collected as gases. And so, based on that one reaction, then we have this. But is it just one reaction? No. Typically laws, people try to find violations of laws. There's something called the laws of thermodynamics, and people have been trying to find violations of laws of thermodynamics for hundreds of years. They haven't found it yet. And so the same thing here, people are trying to find violations. So once they get a law like this, they want to test it. So yeah, sure, the burning candle work, but do other reactions work in the same way? And so you might have heard of the flash bulb one, and some others from Chem 4. Yeah, and it turns out that all the reactions that people observe follow the same pattern, and therefore we call it a law, this reproducible pattern. Laws oftentimes we want to express mathematically. So conservation of mass would be, delta M, the change in mass is equal to 0 for a chemical reaction. But do we want to stop there? What was the hypothesis? What is a hypothesis and a theory? So mass is conserved, but why is it? For example, sure, this pen's going to fall, but why should it fall? Or what is the fundamental reason or description or picture of what's happening there? And so this is what the theory is. The theory is a fundamental description of what's happening. So the fundamental description of why the apple fell is because of the gravitational theory. Well, what about the fundamental description? Why is mass conserved in a chemical reaction? And so the people, you have a law, and we can use the law. We can predict the mass before and the mass after chemical reactions. Very easy. Delta M is equal to 0, right? But then we want something a little bit more. Why is matter behaving in this way? What fundamental, description of matter describes this conservation of mass? And so do you know what the hypothesis was? The hypothesis is that matter is made up of... What is matter made up of? Well, what's the definition of matter? Yeah, anything that has mass and takes up space. So what is matter made up of? Stuff. What is the stuff? What is the stuff that matter is made up of? Atoms, right. And so the hypothesis was that matter is made up of atoms. And that, when you have a chemical reactions, the atoms don't disappear, they're just rearranged in the reaction to form different substances. And so hypothesis, what this is it's a tentative fundamental description. And so the fundamental description, that is, what's happening with the conservation of mass is that we got these things called atoms. And the atoms don't go away or disappear. They're always there. They just get rearranged. It's tentative because, scientists they have to be skeptical in nature because it's part of the scientific method. Scientific method is it's self-policing. All the information has to be rigorously tested, right? In other words, there are going to be people who might have an alternate hypothesis, or people who just want to be absolutely certain that this is the reason why, and we'll try to get this hypothesis to fail in some way. After enough people do that, then we get to the theory. The theory is a fundamental description that has relatively wide acceptance. And so you can just say it's a fundamental description. It has to be widely accepted. That is, it has to have been subjected to tests and scrutiny. And the only way to do it is to try to make it fail. Well, that's what happened with atomic theory. It initially didn't have wide acceptance, and now it pretty much has universal acceptance. There's still people who don't believe in atoms. One of them I met, actually, I think about 5 years ago. He gave me a book about this thick, describing what matter is made up of. And it wasn't atoms, it was something else. His life's work. I think I still have it in my office. But, that's rare. All right, so it's widely accepted. Not only does it have to be widely accepted, a theory has to do one other thing that a hypothesis doesn't. The theory must be able to predict new, unforeseen observations. And so atomic theory, what new unforeseen observations does atomic theory predict? Well, this is in the next chapter, chapter 2. It predicted the law of multiple proportions. If the atoms are just rearranged, then the atoms must combine in some simple whole number ratio. You can't combine like 0.162 parts of this atom with one part of this atom, right? It has to combine in nice multiples of whole numbers. And so that was called the law of multiple proportions. So the atomic theory did predict the law of multiple proportions. All right, so even though we might not get to the hypothesis or theory, or even if the theory hasn't changed, we still look for, these patterns and trends in nature, and then try to use those to help us better understand our current theories or maybe develop new ones. So that's the scientific method there. So let's go back to the first part here of the scientific method, and that is observation. We take measurements. When we observe things, if we don't take measurements, then those observations are very qualitative observations. When we take the measurements, we're taking quantitative observations, right? More precise with numbers. So these measurements, well, what are we measuring? We're measuring properties, right? And what kind of properties are we measuring? Well, what types of properties do we see for matter? There are physical properties. Give me some examples of physical properties. Like mass, like density. Mass is what we call an extensive property. Density is what we call an intensive property. What's the difference between an extensive property and an intensive property?
Or an extensive property is actually dependent on the mass.
On the amount.
On the amount of mass, and for intensive, it's
Independent of the amount. And so we have to be careful. So for example, I might have this liquid in here. This liquid's matter. When we think about matter, matter is made up of atoms, but this is a bit too broad. Let's try to narrow it down. We have some matter in here. And when you look at the matter, how would you characterize this matter? Well, it's a liquid, one. It could be liquid, solid, gas, or plasma. What else could you say about it? Looks like water to me. Looks like water, right? If you're thirsty, would you drink this? Would you? Let's say, let's say there's no water around. You're very thirsty. Then would you drink it? You'd smell it. And after it passes the smell test, then would you drink it? I mean, obviously it smells like gasoline or alcohol. You wouldn't drink it, right? If it smells like water, it's probably okay. Well, this is matter, what do we want to do? Well, we observe the matter. My observations say it's water. It looks like water, smells like water. Next thing is, does it taste like water? Would you? Yeah, those are our observations, right? And so what we do when we take our observations is we want to observe the physical properties and if we have physical properties, what other types of properties are there? Chemical properties of matter. By observing the physical properties and chemical properties of matter, then it can help us identify it, because matter is, can be either a mixture, right, or a substance. And so these are all review terms. So just if they're a little fuzzy, go back and review those. But what's the difference between a mixture and a substance?
Mixture is a combination.
Yeah, mixture is a combination of things, and the composition is variable. Whereas a substance is just made up of one thing, and the composition is fixed. So substance is either a pure, is atom or molecule or compound. But mixtures, the properties can be fixed depending on the composition of the mixture as well. And so one of the ways you can tell a mixture is if it's heterogeneous versus homogeneous. Right? Heterogeneous means it's non-uniform in appearance. If it's non-uniform, obviously it's got to be a mixture. Right? But this looks very uniform. And so since this is homogeneous, it looks very uniform. Does that mean this is water? I mean, I think it's water because this is a water bottle. It's marked H2O here, I think. Well, it's rubbed off a little bit. But how would we know? Well, we got to take very quantitative observations of this. What are the observations and measurements? And so what types of things? Oh, I know. I'm going to weigh how much water I have here. And I got about 35 grams of water. If I get 35 grams of water, does that tell me that this is water? No, 35. What if it was 10 grams? Does it make any difference? No. And so this extensive property, like mass, is not going to tell me anything. I'd rather measure an intensive property like density. If the density of this is 1 gram per milliliter, then would you drink it? Well, I still wouldn't drink it because there could be trace contaminants in here. And trace contaminants could be toxic. And so still I wouldn't want to drink it. And so what we do is we'd measure as many properties as we can to see if those properties match with the properties of water. And after measuring enough properties, then we can get an idea, well, this has got to be pretty pure stuff because everything matches, right? But still, it can be a challenge, measuring all those things. And probably the best thing to do is not to measure all those. The best thing is just get a filtration system and just filter out any impurities you might think are in here. Right? It's probably going to be the most cost-effective way of doing it, and then drink it after that. But we got to watch out because certain things as far as properties go, we want to know, are they intensive versus extensive? So, for example, the density of water. Does the density of water depend on how much water? Let's say you measure the density of 30 gallons of water versus 10 gallons of water. Is the density going to be different? No, it should be the same. And so those we are aware of, and those are just simple things that you keep track of. But things that are more difficult to keep track of are the errors. If I measured a density of 1 gram per milliliter, 1 gram per milliliter, is that a very precise number or not? And so this gets into things of what we call uncertainty and error. Uncertainty and error. And so, for example, 1 gram per milliliter, I don't think is very precise. If somebody told me I measured the density of 1 gram per milliliter, I wouldn't put much weight into that because it's very imprecise. It's imprecise to me because there's a lot of uncertainty in that number. Versus if somebody measured a density of 1.00 grams per milliliter, then I think, okay, all of a sudden I feel that there's a lot less uncertainty there. And so what's the difference? When you look at these two numbers, do you see a glaring difference in uncertainty or not? I see a huge difference in uncertainty between these. And it has to do with precision or it has to do with accuracy. We'll talk about that in a minute. But when I look at a 1 gram per milliliter, I see this degree of uncertainty. This density could be anywhere from 0.6 all the way to 1.4. Let's say, actually not 0.6. Well, we'll just leave it at that. Maybe I shouldn't have used this one because this shouldn't round to 1. But anyway, do you see the degree of uncertainty there? Somebody might get 0.6 and call that, oh, that's close enough to 1. Right? Or somebody might get 1.4 grams per milliliter and say, oh, it's about 1. Whereas over here, the uncertainty, I would say, goes from 0.995 to about 1.004 grams per milliliter. And so these two measurements are totally different. Even though both of them are 1 gram per milliliter, the difference is not, the difference is the uncertainty. And that uncertainty we call precision or accuracy. What is it? Which one is more accurate? 1 or 1.00? Which one is more accurate? Yeah, they're the same. They're both 1, right? And if the true density were 1, then they're both highly accurate. The difference is in precision. Which one's more precise? This one. Usually with higher precision, we hope the accuracy is good, but the accuracy might not be good. The accuracy might not be good because somebody could be very precise and they say, oh, there were exactly 13 people in class today, right? And that's being very precise, but are they very accurate? No, because there's something miscalibrated, in their brain from counting. But here, the same thing can happen. For example, somebody could be spending hours getting the most precise measurement they can on the length. But if the meter stick were left out in the sun and it shrunk, let's say this shrunk a couple of millimeters, even though they're spending hours getting the most precise measurement and get it to the nearest tenth of a millimeter, are they very accurate? No, all their measurements are going to be off. They're going to be off because the meter stick was off. Right? And so accuracy is hard. We don't know. We have no idea, how accurate these are. The only thing we can say is which one's more precise. And the only way to get an idea of the accuracy is to know how those were measured. If we know how those were measured, then we can get a good idea of the accuracy, or a better idea of the accuracy. Was everything calibrated? Was it being measured correctly? Etc. And so we have precision. This precision is given by things, well, sig figs, right? How many sig figs here? 1. How many sig figs there? 3. If I had 20 sig figs, does that mean it's accurate, more accurate? No, it just means it's more precise. And the balance might be really more. Errors we'll talk about more as we go along. But we always want to think about uncertainty in terms of precision and error. What types of errors are there? You guys remember the types of errors you might encounter? One is called a systematic error. You're systematically 2 millimeters too short because the meter stick shrunk with age. Another is called random error. Random error are just these natural fluctuations in values. Systematic error should never be a problem because we, as scientists, should always calibrate our instruments before using them. Random error we can never get rid of. And the only way to get rid of random error is take lots of measurements and then average them. So sometimes you're reading too high, sometimes you're reading too low, but if you take enough, they'll average out. So we're going to look at some of these review topics by working on some problems. I'm going to handle chapter 1 a little differently from the other chapters. In chapter 1, since a lot of it's review, I'm just going to take the liberty to skip a lot of the chapter and just go straight to the homework. And so, scientific method, you can see I signed, I think, all of these or most of these. Classification and properties of matter, some math review, sig figs, units, temperature scales, density, percent composition. All right, what we're going to do is we're going to skip these basic problems and go straight to these, the integrated and advanced exercises, to show you what the difference is between intro chem and chem 1A. Most of the basic problems here are intro chem or chem 4 style questions. It's not until we get to the integrative and advanced that we see things more like chem 1A that we expect. And so let's go to problem number 67 here. According to the rules of significant figures, the product of the measured quantities 99.9 meters and 1.008 meters. And so let's do now 67. We have 99.9 meters times 1.008 meters. Whenever we take a measurement, there's always uncertainty involved in the measurement. And the uncertainty is going to be given by, how precise the measurement is. If you look at these two measurements, do they have roughly the same precision, the same degree of uncertainty in there? No, the degree of uncertainty is quite a bit different. In 99.9, what would you think the range is there, roughly? When you see 99.9 meters, this is a measurement. What on the low side, this could be 99.85 all the way to 99.94. Any measurement in this range would round to 99.9 sig figs. Do you see that? And so what we say is just say roughly 99.9 plus or minus 0.05 roughly. Does that show you this is kind of the degree of uncertainty we expect in this particular measurement here? What about over here? What is the range of values you might see for this that would round to 1.008 meters?
1.0075.
Yeah, this would be 1.0075 to Yeah, 1.0084. And just to keep it simple, we'll just say plus or minus 0.0005 meters. And so which one has a greater degree of uncertainty? The first one or the second one? The greater degree of uncertainty. The first one. There's a lot more uncertainty here. And so when we multiply these two, this one's a much more precise number. When we multiply these two, then we can't have too much precision here because there's some uncertainty in the first one. And so let's go ahead and multiply these and see what we end up with here. But what I want you to do is I want you to ignore sig figs when you do this, and then just go ahead and write more digits than you're allowed. Following the rules of sig figs, we have 3 sig figs here, 4 sig figs here, so our final answer should have how many sig figs? 3. So 99.9 times 1.008 gives us what I want you to do is I want you to write the answer with more digits than you're allowed. Always. And so on tests and quizzes and whatever else, you're going to write, sometimes you can keep track of it. So if you're only allowed 3, you can subscript the extra digit, 6992. And carry a few extra digits, or at least one extra digit. And then show me how you'd round this. So if we were to round this to 3 sig figs, this is meters squared, to 3 sig figs, this should be 101 meters squared. To 3 sig figs. But show me this step, the rounding. I don't want you to just go ahead and write 101. I want to see what you rounded. All right, let's take a look at the degree of uncertainty here. What would you say, plus or minus what? Yeah, this should be plus or minus about 0.5 meters squared. The dimensions are off because these are meter squared. But our final answer should, reflect the same kind of precision, the same kind of uncertainty as the least certain value. And the least certain value is 99.9, which is plus or minus 0.05. When you look at this, answer is plus or minus 0.5. Is that a fair representation of the uncertainty in the measurements? No. It's not. And so this is what the problem here says. Should be expressed as 3 significant figures, 101 meters squared. Yet, in this case, it would be more appropriate to express the result of 4 significant figures, 100.7 meters squared. And so if we express this 4 sig figs, we would get 100, and it would be 0.69. We drop the 9, convert that to a 7, so what is that? 100.7 meters squared. And this turns out to be 4 sig figs, and the reason 4 sig figs should be more appropriate is because the degree of uncertainty in this one is going to be plus or minus 0.05 meters squared. And so this is a more fair representation of the uncertainty that we expect in the final answer versus this. And so this brings us to the difference between a rule and a law. Sig figs, are those the law of significant figures or the rule of significant figures? It's a rule. And rules aren't held to the same rigorous standard that the law would be held to. People, if they try to find holes in the rules for sig figs, they'd find plenty of holes. And like in most cases, when you learn rules, you have to memorize the exceptions. And there are a lot of exceptions for sig figs. And this is one of them. This is a common exception for sig figs where it didn't work. The rules for sig figs fail in this case. It's not a big deal. You haven't had to memorize this scenario. And the reason you haven't had to memorize it because this doesn't come up too often. And if it comes up and you get that, then it's okay. Because they figure that in a year or two, you're going to be doing something called propagation of errors. In propagation of errors, you forget all the rules you learned for sig figs and you follow a new set of rules. And the new set of rules will more accurately calculate the uncertainty in products, division, etc. And so the reason not much is made out of this is just because of that. You're going to do a much more rigorous mathematical way of doing that. Still, we do sig figs, of course, but how we handle these uncertainties is totally different. It's not hard, you know. It's actually quite easy. You know, what percent is that? You know, 5 out of whatever. 5 out of this. What percent is that? The bigger the percentage, you know, there's a bigger percentage uncertainty, and that percentage uncertainty should be reflected over here as well. Let's move on. Anyway, I'm not going to spend much time talking or reviewing sig fig rules. They're pretty easy to review. Once you forgot them, it shouldn't take you very long to figure them out again. All right, let's go to number 68. For a solution containing 6.38% paradichlorobenzene by mass in benzene, the density of the solution as a function of temperature in the temperature range 15 to 65 degrees C is given by the equation here. And so density changes with temperature. You know, the density of water changes as the temperature changes. And so what we do is this. Here we have this equation. Where did this equation come from? Well, equations like this that you often see are a result of something like this. Let me give you another example of an equation. Heat equals nRT. Equation. Where did this equation come from? Well, everybody recognizes this. This is called the ideal gas law. And so we're at the law, but where did this law originate from? Where did the law originate from? Where did it come from? Did the law come from theory, you know, atomic theory, how atoms interact? Maybe this law was a prediction of atomic theory. You know, somebody predicted, based on the behavior of atoms, gases should behave like this, and came up with this law that they called the ideal gas law. Is that where the ideal gas law came from? Where do you think the ideal gas law came from? For example, what is this R? Oh, everybody has R memorized. Do you have R memorized? Maybe not. It's been a long summer.
Yeah.
Okay. 8, 2, 06. Oh. Usually people have it memorized to 3 sig figs in Chem 4, but it's good. You have 4 sig figs, liters, atmosphere, per mole, Kelvin. This is an ATM. Where did this come from? Where did the R come from? Tell me what fundamental part of atoms we can get R from. This is one of the reasons why I had such a hard time in thermo. Because when I was taking general chem, I had no problem. This equation is so easy. You got a calculator, punch in the numbers, spit out the answer, no problem. And so I had no problem doing ideal gas law calculations. I can do them day and night. They're easy. I like them because they're easy. Right? But when people started asking me things like this, you know, what's the origin of R? Where does R come from? Where did it come from? Where did this law come from? Then I had started having trouble. Because all of a sudden you expect me to know that? I don't know. I just know how to punch in the numbers and spit out the answer. And so that's one, my way of thinking was totally different than some of the others, Some of the top students in the class didn't think that way. They thought a little differently. And so anyway, where did this come from? Well, this, actually, where did this come from? This came from observations of trends and patterns. Just observe. You take some measurements. How does a gas behave? Where does this R come from? This R comes from is just like some fudge factor, some constant that you have to plug in there to make this equation work. And so basically, this is what we call an empirical equation. We see empirical equations a lot in science. Do you know what empirical means? Empirical means based on observation. So this is a mathematical equation that came from observation. So somebody collected a lot of data and tried to fit that data to a mathematical equation and came up with this. Well, this equation is the exact same thing. This is an empirical equation. Where did this equation come from? Well, this equation must have come from observations. You probably have you've probably seen data tables like this, where they have the temperature versus the density. For water, for example. You might have done a density of water experiment in intro chem, where you measure the temperature of the water and you use this table to figure out what is the density of water at that particular temperature. Have you done that? And so you got a whole bunch of temperatures here, a whole bunch of densities, right? And so one way we can use this data is just, we have some temperature here, and if it matches, we got some density there. But if we have a temperature here between 2 points, then we have to estimate the density over here. Have you done that kind of stuff? And so we use a data table like this. But oftentimes what's easier is to graph it out. If we plot this, then we can see the density of water or density of some liquid over time. And so this is the density of para-dichlorobenzene. It looks like as the temperature increases, this little t increases, is negative, it becomes more negative, which means the density should shrink. Unless the temperature is below 15, and then the density increases. It's a funky equation. And so, we get some kind of data like this. Density decreasing. And so we get a pattern here, which we can recognize, like a linear pattern. And then, we got a bunch of data like this, we can just draw a line. So that the data follows that trend. We can call it a trend line. Okay, so we get that, and then we can use this graph. For example, if we have this density, what's the temperature? Well, we can figure it out based on the graph. The temperature should be that. Or if we have this temperature, what is the density? Work backwards like that. But what is the more concise way of doing this is, not to have a big data table like this, not to have a big graph like this, but the most concise way of doing that is to define this by a mathematical equation. The mathematical equation is going to be the most concise and precise way to define this term. So we'll have something like this, y equals mx plus b, perhaps, although that doesn't quite fit it exactly. But then once we get this, then we see y is the density. The density is the slope times x, which is the temperature, plus b. And this we call an empirical equation. We have lots of these empirical equations. And those oftentimes we call laws. So for example, there's something called Charles' law, right? Boyle's law, Gay-Lussac's law. All those laws put together made the ideal gas law. So we have those. Well, here we have another empirical equation here. Now, the thing is, we're always thinking about uncertainty. So if you're just given an equation, you don't know, how much data was collected. And so we got to think about this too. So for example, let's say somebody collects 1,000 data points. That's a lot of data, right? Take 1,000 different measurements and then plot those out. You're going to expect good precision. But if somebody takes 2 data points, they say, I don't have time. I don't want to do the work. And they just take one temperature here, T1, and the second temperature here, T2, and they get 2 data points. Are you going to have as much confidence in that? No. You aren't. And so we got to have a way of dealing with this uncertainty. We aren't dealing with it just yet because here we've given this equation, we don't know how much. How much confidence we should have in that particular equation. For example, is this mathematical equation an exact fit of the data or just a rough fit? The data. Etc. Well, those types of things we're going to look at as we go along. Since we're always dealing with measurements, we got to start incorporating this kind of thinking into those measurements. But we'll just build it up with time. So for right now, we're just going to take this equation and assume it works okay between 15 and 65. Now, there's a fairly good degree of precision here because looking at the number of digits here and here, you can see that. But let's go ahead and deal with this. At what temperature will the solution have a density of 1.543 grams per milliliter? So now we have some kind of empirical equation. We could call this the law of the density of benzene. It would be a law if enough people tested and then we got plenty of data so that we can have some decent confidence in this. But what is the temperature? Can somebody calculate it? And so the density is 1.543 grams per milliliter. This is equal to 1.5794 minus 1.836 times 10 to the minus 3, T minus 15. This equation is starting to look like what we call an engineering equation. A lot of engineers, they don't want to waste a lot of time, looking at the units and doing this. Usually what they do in the engineering equation is combine all the constants, get rid of the units and just have a variable, a single variable, you just punch it in, and that's it. And so you have to watch out. For our chemists, we don't like this. For example, here, where are the units? What are the units here? Do you see any units here? I don't like this equation at all because there are no units. It doesn't make sense. But we'll treat this as an engineering equation and just try to use it. And so we got 1.543 and solve for the temperature. And so the first thing is we have to add or subtract, right? What do you want to do? Let's add this to both sides. Can we do that? And subtract this from both sides. And so I got 1.836 times 10 to the minus 3 T minus 15. I'm going to subtract this from both sides. I got 1.5794 minus 1.543. Now the reason I write it like this is because when we subtract, we don't look at the number of sig figs, we look at the number of decimal places. And so over here I'm allowed 3 decimal places because I have better precision here, but over here, the uncertain digit is the 3rd decimal place. And so doing the subtraction, I got 4 minus 0 is 4, 9 minus 3 is 6, 7 minus 4 is 3, 0, 0. And so I get 0.0364. So I have 5 sig figs here. I have 4 sig figs here, but my final answer is only allowed how many sig figs? I only have 2 sig figs for my final answer here. And it's because of the number of decimal places. And this makes sense because here it's 1.543 plus or minus 0.0005. This would be 0.0364 plus or minus 0.0005. Does that make sense? That's the degree of uncertainty there. And so I get 0.0364, and then I'm going to divide this here. And so when I do a division, I have 4 sig figs and 2 sig figs. And I've got to keep track of my sig figs. This is t minus 15. This is going to equal 0.0364. I'm going to carry this digit. Why don't I just round it off? The reason I don't round it off is because I want to minimize something called round-off error. Let's say this is it. Let's say you were due, you're due 1.4% interest on your savings account. But let's say every day somebody just decides to round it to 1%. Every day. You said, okay, 1.4%, I'm going to round it down to 1%. Would you be happy? No, because you end up, by the end of the year, you'd end up earning a lot less interest, right? Well, the same thing happens in calculations. If you round off in the middle of a calculation, let's say, you know what, I'm going to get rid of this digit. I'm going to get rid of that digit. By the end of the calculation, your final answer is going to be potentially way off. Right? And so we don't round off on intermediate steps. We round off at the end. So I'm going to carry extra digits. This is going to be divided by 1.836 times 10 to the minus 3. And so how many sig figs am I allowed in this division here? 2. And so I get, actually, am I out of time? How late do we go till? 3:25. 3:25? Oops. Oh, okay. Sorry, I thought we went to 3:35 for some reason. Okay, let me stop here. No wonder I got ahead. So, sorry, I kept you an extra 10. I'll let you out for a minute.